Okay, yeah, thank you. I would like to welcome you to today's webinar. So, as Gary told, my name is Denis Funk. I'm supporting FLEXIM GmbH in market management, focusing on power generation and water industry. I'm pleased that you're participating in today's live webinar, in which I like to talk about cost-efficient flow monitoring solutions of water mains. You're all muted. At the end, we will have time for questions and discussions. Therefore, I would like to request you to use the chat box. So first things first, the agenda. So let us start with a short introduction of the company and the measurement principle of today's focused on flow measurement technology. Understanding the principle helps to understand the advantages as well as the challenges and solutions we will dive into afterwards. FLEXIM is a German company which develops, is doing research and manufactures and sells non-invasive flow metering solutions. It began in 1990. 4 graduates of the Humboldt University in Berlin and University in Rostock founded the company FLEXIM GmbH. FLEXIM, which abbreviates in German Flexible Industriemesstechnik, means flexible industrial measuring solutions. It started in a flat at the back of a typical old building in Berlin. They developed a portable clamp-on ultrasonic flow meter. 2 years later, they launched this flow meter as their first product under the name ADM64R2. The 4 founders are still part of the company. Since more than 30 years, they're actively pushing the development of the company and especially their products and being part of the company's R&D. You can see all these 4 founders at the bottom of the slide. There's a nice picture. Within the last 30 years, FLEXIM became a medium-sized global player. Today, FLEXIM, we are 450 FLEXIMers working at the headquarters in Berlin, where I'm located as well, and numerous subsidiaries worldwide. So the product portfolio ranges from portable to stationary flow measurement solutions for liquid, gases, and since last year as well for steam. So let us have a look on the measurement principle. So how we measure it is based on the transit time difference principle. Here you can see a picture of a pipe where 2 transducers are mounted onto. So an ultrasonic clamp-on flow meter is usually consisting of a transmitter, which we cannot see here on the slide, and at least 1 pair of transducers and mounting assemblies. The transducers shown here at the top of the pipe are coupled onto the pipe. Ultrasonic signals sent through the pipe and media from one transducer reflected by the pipe wall here at the bottom and caught by the opponent transducer, which is acting as a receiver, and vice versa. So the time the ultrasonic signal travels from one transducer through the pipe called transit time. So the ultrasonic signals are sent alternating in and against the flow direction. The signals with the flow direction of the media are faster than the signals against the flow. So like a swimmer who's swimming against or with the current. The difference of the transit times is proportional to the flow velocity of the fluid. Considering as well the cross-section of the pipe, the volume flow can be calculated. The flow measurement system is a refractive system. This means that the ultrasonic signal, which is traveling through at least 3 different phases, so the transducer wedge, the pipe, and the fluid, with different characteristics. Each of these materials have different characteristics. When I talk about characteristics here, then I mean specific the sound speed. It is refracted in a certain angle at each phase transition. So multiplied by the acoustical calibration factor K alpha brings the sound speed of the medium in correlation with the angle of the ultrasonic beam into the calculation. What does it mean? It means that each material which is in action here, like the wedge material, the pipe material, and also the fluid, is having its own specific sound speed. And according to these sound speeds on the transition phases, the ultrasonic signal is refracted in a certain angle. And this is considered in the volume flow calculation. Please remember this. We will come to this later when we have a look on the challenges. And to include the flow profile of different fluids into the calculation, the fluid mechanical calibration factor K Reynolds is added. Today we are focused on water mains, so the media is set as water. Just a short clip to see the measurement in action, to visualize it a bit more in detail. So we have here the same transducer layout. So in reflect mode, 2 transducers mounted onto the pipe, and 2 sound passes are between the transducers. Here you can see that one signal is traveling faster than the other, resulting in a transit time difference, which is the basis for this measurement technology we are focusing on today. So why cost-efficient solution? So it may be that some of you had already contact with inline meters, mag meters, as well as non-invasive flow measurement solutions like ultrasonic clamp-on meters. And might be that some of you would say the clamp-on meter is usually not the cheapest on the market. This depends on the view. So first of all, I would partially agree with this statement and say, okay, on the water applications, especially on small pipelines, there might be the certain mag meter more competitive when it comes to purchasing costs. So purchasing costs, we are talking here about purchasing costs. Today I want to put the focus a bit more on the installation cost, because on the purchasing cost it is very transparent, we can see it, and it is not often the installation costs are not often considered as well like the purchasing costs. So that's why it's the cost efficient solution when we focus on the whole package, so the purchasing cost and the installation cost, which have to be considered for the implementation of such flow meters. Now I won't go through slides and mention the differences between inliners and non-invasive ultrasonic flow meters when it comes to the implementation phase, so the installation, or also the installation effort or costs. So starting with the planning, when you want to implement a flow meter, especially inline flow meter, you have to plan the implementation very well. You have to consider the effects, and you have to consider what kind of mains or lines have to be shut off, and what consequences you have to face. And usually implementing a mag meter or inliner or other inline flow meters, you have to shut off the line, and then you have to consider bypasses, or at least some supply interruption. And the supply interruption, you have also to communicate to some households and users in a certain zone if this is affected, if you don't have a bypass. Afterwards, for sure, the major part is the installation. So installation of the flow meter is also differing. On an inline meter, usually you have to shut off the pipe. This is the first, or excavate, or depending if it's buried or not, and shut off the pipe, cut the pipe usually, welding flanges, and installing the flow meter. Welding flanges and cutting the pipe when we consider a new installation. If you do a one-by-one replacement, then it might differ, but now we are considering a new installation, so we have to cut the pipe, welding the flanges, and installing the flow meter. And on these nice exemplary pictures here, we see nice, small pipes. It's not really often water mains. Water mains usually are bigger, so considering a DN600 or DN800 line, then even the installing the flow meter, so the putting a big inline meter in place needs pretty big effort, some stuff, heavy lifting equipment to put this in place. Coming to the end of the implementation, so everything is set, the flow meter is in place, is commissioned. Then we have to reopen the pipe, ensure the supply again, and flush the pipe because we have done intrusive works. For sure, the ultrasonic flow meter needs as well work. Once the pipe is accessible, we have to determine the pipe parameters, especially like circumferences, pipe material, wall thickness, and then we have to install the transducers properly with the proper transducer distance, and then we have also to connect the transducers to the transmitter, and the transmitter into the junction box, and start the measurement. I did just focus here on the differences. So some of you may say, okay, we have here to consider as well the excavation, and yeah, this I agreed, sure, we have to consider also the excavation and other works, but these are the same for both techniques, just focusing on the differences. And then it comes up to mind that the installation of a non-invasive flow meter is definitely less effort and lower in cost than an inline meter. So coming to the implementation on water mains, the next bigger topic for today, I would like to focus on some challenges and solutions for sure. For non-invasive flow measurement, we have to face challenges as well, and different challenges than mag meters or inliners maybe, and as well also different challenges in the water industry than in other industries. So having here a nice chamber, a wet chamber installation from Australia, a water main line, and we can see these are wet chambers which are flooded and affecting the transducer mounting as well as the transducers itself with harsh environmental conditions. So these conditions are not, or usually can be not found in other industries like oil and gas, chemical, or power generation. It is very unique to the water industry to have these challenging, harsh conditions, as well like these buried installations, the transducers, the equipment is flooded, submerged. So basically, when I talk about equipment here, then I mean mainly the transducers and the assembly material, because the transmitter is usually placed not close to the transducers in this installation. So what is the solution, or these challenges are faced by all non-invasive clamp-on manufacturers, and every clamp-on manufacturer has to deal with these challenges and find some solutions. And for sure, every transducer or every manufacturer have to make his transducers sealed and prevent ingress of dust and also water to ensure the proper function. So we're providing IP68 options and having a fully sealed transducer design. On the right side you can see, and there are no connectors, so the cable are firmly connected to the transducer body itself. And on the other hand, the transducer is just one part. The mounting have to be also tamper-proven, robust, and long-term stable, because once you have buried, the transducers should stay in place and with the right distance you have commissioned the transducers with, and they have to be ensured that small sediments, rocks, parts also at the filling process are not unlining the transducer. So we are coming with a rail. The most manufacturers using a rail where they put their transducers in, and then you can screw them onto the pipe, firmly connected, pushed down onto the pipe for coupling to the pipe. And then they ensure, some of them provide a cover. We are doing a stainless steel cover to ensure that no big particles or sediments are hitting the transducers, unlining them, because this is one of the most important parts in the filling process to ensure that the installation is robust and is not unlined. Another part of the installation itself is the coupling. So coupling means the connection between the transducer to the pipe. It is very important because we want to ensure a proper and stable injection of the ultrasound signal into the pipe and the fluid. So the coupling of the transducer to the pipe with a permanent coupling pad is recommended from our side, from our view and experiences, because there are different coupling methods like paste, gel, or grease, and dry coupling like these pads. But especially for these applications we are focusing on today, like water mains in the water industry, dry coupling is necessary, is deemed necessary, because a lot of these installations are buried or very remote. So these applications itself demand maintenance-free equipment. Just a short impression how we do our stress test. Just kidding, but it's a typical application before the filling process. The transducers are mounted and in these boxes, which shall ensure proper alignment and long-term stable installation. So another challenge is as well the ambient conditions, or are the ambient conditions. So ambient temperature fluctuations. So how can this affect the measurement? We will see this in a couple of seconds. So but when we consider outdoor installations, so when we're not considering chambers, wet chambers, or covered installations by buildings or buried installation, we also face water mains which are installed outdoor. We have to deal with the typical ambient conditions like temperature, and temperature fluctuations are influencing the measurement itself. So here we can see a nice installation from our Southeast Asian colleagues on a water main supply line, and these are totally exposed to ambient environment, and how this affects the measurement we will see on the next slide, because the asthma guideline already described it, and they are describing the effect as well and suggest compensation, temperature compensation. So what is the deal about it? So the uncertainty of a measurement is affected by the sound speed of liquid and the materials the ultrasonic pulse is traveling through. This is what I meant at the beginning. We have to remember or keep in mind it for now. So every material has a different or specific sound of speed. So, and this is changing with temperature. So as we can remember from the introduction, the transit time technology, the measurement of the flow velocity is depending on the transit time difference and the acoustic calibration factor. So the K alpha is displaying the acoustic angle and sound speed. So ambient temperature changes, meaning also material temperature changes, and also transducer wedges temperature changes. And this changes resulting in changes of the sound speed of the material. So of the pipe material, of the wedge material, or sometimes also of the fluid. And this is raising uncertainty because we're changing the refraction angle, how the signal is going through the pipe and through the fluid. And this should be compensated, and asthma described this as well in their guideline, asthma MFC 5.1. And we found a solution how we do it. It's a typical solution to do it. It's on other field instrumentation, but on ultrasonic clamp on, it's a rare approach, but we face these challenges often with this temperature fluctuations on our applications, and from our experience, it is working. From laboratory tests in the PDB, we confirmed the function of this approach, of this feature. So we are integrating temperature probes, temperature sensors, and the transducer wedges itself. And what is important here, and the important approach is that we integrate the temperature sensors in each transducer wedge of one pair. So one pair is always consisting of at least two transducer wedges. And it is important to have transducer or temperature sensors in each transducer head, in each transducer wedge. So what can happen? We have seen this slide before. Here we can identify, okay, this is what we learned at the beginning, the reflect mode. We have on one side both transducers sitting. So these transducers usually affected by day and night temperature fluctuations, but when we have to go with a layout with one sound pass or three sound pass, then one transducer would sit on the other side of the pipe, and then it could be even at the same time that one transducer is sitting in the shadow and the other is exposed to sunlight, and we get easily 10 to 20 Kelvin temperature difference. So, and then we have a local temperature difference, and this is just to be compensated when you have in each transducer a wedge temperature probe. Coming to another challenge, which is typical for the water industry, is that we are facing very huge variety of pipe materials and pipe dimensions. Here we can see a big water supply line left in Southeast Asia, and the right one is as well in Southeast Asia located. Big water supply lines with challenging material, PCCP, on the right side. And so we have a huge variety of wall thicknesses and pipe outer diameters and materials, which can challenge the ultrasonic non-invasive flow measurement technology. And what we experienced is that for sure different frequencies are beneficial. Usually, a manufacturer is providing transducers, a bunch of transducers in different frequencies to ensure best fitting frequency for each application, for each pipe size. But as well, we have learned from our experience that it's very beneficial to go with two techniques. So to explain it shortly, we have to jump into the basics shortly. So there are two common techniques to send the ultrasonic signal through the pipe and media. So the one is lamp wave and the other shear wave. So shear wave, on the left side displayed, the technology is the most popular on the clamp-on market. The shear wave transducers operating with transversal waves. So such ultrasonic waves transmitted by the transducer into the pipe wall. The waves are reflected in the pipe wall and transmitted as well into the water. So the lamp wave on the right side displayed transducers generating an ultrasonic pipe wall resonance, so which generated in the pipe material and moving along the pipe. The pipe is emitting the lamp wave into the water. The advantage of a lamp wave is the broad signal, which is less sensitive to high flow velocities, beam shifts, impurities, and both technologies based on the transit time principle, but are different approaches how to emit the ultrasonic signal and how to do the signal propagation. As you can already read, the shear wave is usually the go-to technology or go-to technique for the most liquid applications. And the lamp wave is rather used for gaseous applications. But from our experience, we can say that especially for very heavily sedimented or aerated flows or high flow velocities, especially in combination with big pipes, it is very beneficial to use the lamp wave, because sometimes the shear wave are limited then. So the last topic for today, I want to focus on uncertainty and repeatability. So speaking about uncertainty, when we talk about non-invasive flow measurement, generally it should be different between measuring system and measurement at the field application. So the measurement uncertainty of our Fluxus F71. This is our main flow solution for liquid applications is 0.3%. So considering the uncertainty in the field, we have to take also into account other uncertainties, for example, of the application, like the pipe roughness, the circumferences, the composition of the pipe material, and then we have to state measurement or an uncertainty of the measurement at the application, and then we state 1%. So considering all these tolerances of circumferences or unknown wall thicknesses, composition of pipe material tolerances. So for sure, if we would have a perfect known application, we could state also the measuring system uncertainty of 0.3%, but in real life, we have always some tolerances in the application parameters. So what we are doing is we are calibrating our systems in the factory, and here we have a modular approach so that we are calibrating our transmitters and transducers independently, and each of these parts is getting a calibration certificate so that you can use each and that you can use a system and for example replace a transducer pair or a transmitter, and you're still having a calibrated system or calibrated loop. Just a small teaser, if you like this presentation and afterwards you want to see how we calibrate our systems, it's a very nice small short clip on YouTube available. So because we are doing also the wet calibration rig, as the most of you I guess are aware, so on a wet calibration rig, but we have also aperture calibration. Is a very unique transducer calibration for clamp-on ultrasonic flow meters, and I would like to recommend this small short clip to you to get an impression how we do it, and what is so unique on it, and why is it a nice way to calibrate or smart way to calibrate. So just the last slide for today. So I just want to tell you also a bit about our in-house weddings. So we are doing almost every day in-house weddings, and when I talk about wedding, I'm talking about matching the piezo crystals. So how we can ensure such nice competitive uncertainties especially for transducers. We are using a method called wedding. So we take the core part of each transducer. It's the piezo crystal, and the piezo crystal has each piezo crystal is having slightly different characteristics, electronic characteristics, and these characteristics we are determining on a bigger batch of crystals, and then we match each piezo crystal, which is matching the best together, and so we can ensure or maximize the measurement performance and also the low flow resolution. So I would like to thank you for your attention.